Let's move on and talk about another vertical motion known as free rise. Here, the golf ball is bouncing up from the floor. And again, this is in slow motion. Free rise is the rising motion of an object when gravity is the only force acting on it. So once this golf ball left the floor, as it went up in the air, the only force acting on it was gravity. It too is uniform, aka constant acceleration. For free rise to occur, the object has to be launched with an initial velocity greater than zero in the positive direction. As with free fall, when we have free rise, we're assuming the air resistance is very small, small enough that we can ignore it. Notice, as time goes on, these dots represent every 5/100ths of a second, and we can see initially the displacement or change in position during the first 5/100ths of a second is pretty large, but as time goes on, the displacement gets smaller and smaller, and eventually the ball briefly comes to a stop at its peak height. Let's look at the position time graph for free rise. We've seen this before, a curve that goes from steeper slope to flatter slope, and that's a sign of an object that's slowing down. Looking at the table, we can see the position continues to increase, but the amount that the displacement changes is getting smaller and smaller. In fact, 24.5 millimeters smaller every 5/100ths of a second. Looking at our velocity timeline, we can see that it starts away from the time axis and heads towards zero, an indication that it's slowing down, and it's a straight line with a constant slope. If we take a look at our time velocity and change in velocity chart, we can see that every 5/100ths of a second, the velocity is changing by 4.9 meters per second in the negative direction. And so the change in velocity is constant as the object slows down. Let's look at free rise in the general sense. The acceleration tells us the changes in velocity and position, just like it did for free fall. Velocity. Every second the velocity changes by the amount of the acceleration. For displacement, during the first second, the displacement is the initial velocity minus half of the amount of the acceleration. And then every second after that, the displacement changes by the amount of the acceleration. So let's take a look at free rise on Earth. The acceleration due to gravity is 9.8 meters per second squared in the negative direction. And for this specific example, we're going to start with an initial velocity of 49 meters per second in the positive direction. So here's our table showing time, velocity, displacement, and position. As time goes on, you can see every second the velocity is changing. In this case, it's decreasing by 9.8 meters per second. And then if we look at the displacement, the initial displacement is 49 minus half of the acceleration, which is 4.9, and that gives us a displacement of 44.1 meters. And then we can see every second that goes by, the displacement is going to decrease by 9.8 meters every second. And we can see that in this case, the object reached a peak height of 122.5 meters. Now, let's have you try your hand at filling out the time, velocity, displacement, and position table for free rise on the moon. So at time zero, we have an initial velocity of 8 meters per second in the positive direction and a starting position of 0 meters. The acceleration on the moon is 1.6 meters per second squared in the negative direction. Pause the video and take a few minutes to complete this table. All finished? Let's see how you did. So the acceleration is -6 meters per second squared, so the velocity is going to decrease by 1.6 meters per second every second. And the displacement is going to start out by being the velocity minus half of the acceleration. So that's going to be a displacement of 7.2 meters. And then the displacement is going to decrease by 1.6 meters every second after that. And of course, you can find the position by simply taking the displacement and adding it to the previous position. Okay, let's move on and tackle another challenge. Let's calculate the free rise on Jupiter, where the acceleration is negative 25 meters per second squared. Here, the object has an initial velocity in the positive direction of 125 meters per second, and the starting position is 0. Pause the video and take a few minutes to complete this table. Are you finished? Well, let's take a look. Because the acceleration was 25 meters per second in the negative direction, the velocity is going to decrease by 25 meters a second every second until it reaches 0. Our displacement is going to be the initial velocity minus half the acceleration, so that will give us 112.5 meters as the displacement during the first second. And then after that, the displacement is going to decrease by 25 meters every subsequent second. And we can see this object reaches its peak height of 312.5 meters in 5 seconds. Let's move on to vertical projectile motion. Here we see the golf ball bouncing up in slow motion, reaching its peak, and speeding back down towards the floor. This is what's known as vertical projectile motion. It's the combination of free rise and free fall. In this case, the object has to be launched with an initial velocity greater than 0 in the positive direction. And once the object is launched, gravity is the only force acting on it. It's uniform acceleration, and once again, air resistance is very small, so small that we can ignore it. Well, let's take a look at the position time graph. Not surprisingly, it is this arch shape that we've seen before when we've pushed something up a hill and let it roll back down. We can see a line of symmetry here at half a second. This first part, the object is slowing down. It is in free rise. It reaches its peak and momentarily stops moving, and then it speeds up as it heads down towards the floor. This line here at half a second is a symmetry of position. Notice these positions are all the same when you're equal distance from this line of symmetry. Now let's take a look at the velocity time graph, and we can see here that we start with an initial velocity of just under 5 meters per second. We slow down, we reach 0 meters per second, change directions, and then speed up in the negative direction as the object is heading down. And we reach a final velocity when it hits the floor of 4.9 meters per second in the negative direction. There is a line of symmetry here also. It's perpendicular to our velocity line, and it too happens at half a second. But notice these velocities, as you move away from the line of symmetry, these velocities are the same speed, just in the opposite direction. So their number values are the same, it's just that they're headed in the opposite direction. The initial velocity that an object is launched with will be the velocity that it returns back to the floor, only in the negative direction.